Hello, welcome back to part 4 of the topic dynamics of a particle in the first course in general physics. In this lecture, we will continue dealing with the topic of work and energy, and we will discuss the work done by a variable force. In the previous lecture, we have discussed how to calculate the work done by a constant force. And in this lecture, we will develop methods of determining and calculating the energy, the work done by a variable force on the object. Then we will go on to discuss the rate of change of work, the rate at which work is done, which is the power. We will define it. After that, we will move to another topic, which is the discussion of another type of energy, specifically called the potential energy. And we will discuss the different methods of calculating this energy and the different aspects of it. And hopefully in the next lecture, we will be arriving at the law of conservation of energy, mechanical energy and total energy. But before that, in this lecture, we will discuss key points related to the development of this principle, the conservation of energy. One of them is the categorization and the classification of forces into two types: conservative forces, which conserve mechanical energy, and non-conservative forces, which do not conserve mechanical energy or lead to a waste in mechanical energy. And then we will talk about the potential energy in various aspects of it. The first step in this lecture is to discuss the work done by a variable force. And as a special case and a simple case, we will consider the one-dimensional case. The one-dimensional case is the case by which the variable force and the motion of the object are directed along the x-axis, either left or right, but they are along the x-axis, along a straight line, of course, but for simplicity, for convenience, we call that line x. We can, of course, call it y. We can call it any other name. But for simplicity, we assume that the motion takes place along the x-axis, and the force also is directed along the x-axis. This is the case where we have a one-dimensional case. Previously, we have developed the method for calculating the work done by a constant force on an object. If the force and the displacement are in the same direction along the same line, then the previously developed or defined formula for the work tells us that the work done by such a force, which acts along the same line of the displacement, is equal to the magnitude of the force times the displacement, simply F times delta x if we call the displacement delta x. We have called it d in the previous lecture. It's the same thing. It's just another name. Now, accordingly, we have only one way of defining the work, which is the work done by a constant force. The force in hand is variable. So what do we do? How do we calculate the work done by this force? We have, in this case, to develop a new technique in order to be able to apply the previous definition to our work. So what do we do is we cut down the axis or the straight line along which the object moves into small intervals, very small intervals. We call each one of them delta x, and we make that delta x so small up to the point that the force acting on the object during this displacement delta x is almost constant. So in that case, we will have a constant force or almost a constant force acting during the motion of an object, a displacement delta x. In that sense, we can apply the previous definition of work to the motion of the object during this particularly small displacement delta x, because the force is almost constant. So the work done by the force during the displacement delta x is simply the force in that displacement times the displacement itself, the force times the displacement, because they are both working on the same line. So the angle phi is 0 between them, or 180 degrees. If it is 180 degrees, then delta x would be negative and will give a negative sign for the work. If the angle is 0, then delta x would be positive, assuming that f is in the positive direction. So f, and we have written sub j to indicate the number of the interval, because the total displacement is sectioned into a number of displacements, small displacements delta x. The first one is the first delta x, the second one is the second delta x, and so on. Since the force is variable, then the magnitude of the force in the first displacement is different than the magnitude of the force in the second displacement, and so on. So f changes from one displacement to another. So the work delta w sub j done by the force in the interval which has a number j is equal to f sub j of x times delta x. F of x means that the force is dependent on the x-axis only, on the x variable only. So delta w sub j is the work done by the force during that very small interval. In order to obtain the total work done by the variable force from the beginning of the motion to the end of the motion, we add the work done during each interval. We calculate the work done in each interval and add them together, and thus we get the total work done by the force during the total motion of the object. So we reach this, or we obtain this formula, which says that the work done is the summation over j over the intervals, the different intervals, of f sub j of x times delta x. That will give us the total work done by the variable force in moving the object given displacement. Now, we might encounter a situation where the force varies continuously with x as the object moves, which means that we know the force as a function of x. If the force is changing continuously with x, then we have to take the displacement, infinitesimal displacement delta x, we have to take it so small in order to make sure that the force during that displacement in the calculation is constant, because we have to make sure that the force is constant in order to be able to apply our previous definition of the work. If the force is constant, is constantly varying or continuously varying, that means delta x should go to 0, should be chosen to be infinitesimally small or approaching 0. In this case, delta x would go to dx. And we apply the same definition as previously defined, but in this case, the work done during an infinitesimal displacement dx is simply f of x, the value of x at that position, times dx, times the displacement dx. That is the work done during the infinitesimal displacement. And in order to obtain the total work done from the beginning of the motion to the end of the motion, we integrate, that is the summation, it is equivalent to summation, we integrate this quantity f of x dx from x sub I, which is the initial position of the particle, to x sub f, which is the final position of the particle. Now, if we know the force, the variable force, as a function of x, then handling this integral would be somehow easy or difficult depending on f of x, but it is an integral to be calculated. And if we can calculate it analytically, if the function f of x is simple, then we can calculate this integral in a simple way if the force f of x turns out to be a difficult function of position, then we have to adopt probably some numerical methods to calculate this integral, and either way we obtain the work done by this force during the motion of the object from x initial to x final. So this is the one-dimensional case. The three-dimensional case is a generalization to this development, where in this case we have three components for the force. These components are f sub x in the x direction, f sub y in the y direction, and f sub z in the z direction. And also, the displacement is in general a three-dimensional displacement in space. Thus, the infinitesimal displacement dr would have three components: dx in the x direction, dy in the y direction, and dz in the z direction. And when we apply the definition of work, which is f dot the displacement dr during this small interval of the displacement, the dot product will give us f sub x dx plus f sub y dy plus f sub z dz, as we have mentioned in the context of discussing the vector analysis. The dot product would give you the sum of the products of the similar components of the two vectors that has been multiplied through the dot product. So in this case, if we have a three-dimensional force and the object is moving in three-dimensional space in general, we will have the general formula. The work done by this three-dimensional force is equal to the integral from x initial to x final f of f sub x dx plus the integral from y initial to y final f sub y dy plus the integral from z initial to z final f sub z dz. Now, these coordinates x initial, y initial, z initial are the x, y, and z coordinates in the initial state, in the initial position of the particle. It is simply r sub I, r vector, the position vector sub I, the initial position of the particle. And x sub f, y sub f, and z sub f are the coordinates of the final position, r sub f, of the particle. Of course, in looking at this formula, we can have the force with only one component. We could have a one component force, supposedly f sub x only is non-zero, and f sub y and f sub z is 0, then we will get a case which is similar to the one-dimensional case. Similarly, if we have f sub y is non-zero and the rest of the components are zeros, we have a one-dimensional case where the object moves in the y direction. And similarly, if f sub z is non-zero and the rest of the components of the force are 0, then we have again a one-dimensional case, where the object would be accelerated in the z direction due to the force in that direction. Similarly, we may have a force that is directed in a general direction in space with three components, but the object only moves along one direction. Suppose that the object, under the influence of the three-dimensional force, if the object moves along the x-axis, then dy and dz are zeros in this case, and again we obtain the one-dimensional case that we have discussed previously. So this is a general formula that is applied to any motion of the object along any trajectory and under the influence of any force. But of course, the force and the relative direction of the force to the trajectory of the object would give us, for example, a simple problem to solve, a simple integral to evaluate, or a more difficult, depending on the formula of the force and on the relative orientation of the force with respect to the trajectory of the object. As an example, let's discuss the work done by a spring force, which is an application of the one-dimensional case for calculating the work done by a variable force. The spring force is a restoring force, which means that if we attach an object to one end of the spring, the other end being fixed on a wall, for example, or something, or a table or something. And if we pull on the object that's attached to the free end of the spring, the spring force tends to pull on the object back. If we let go, the object would go back, would tend to go back to its initial position. In that sense, the force is restoring. It always tends to get the object back. And experimentally, a specific type of springs obey a force law which is called Hooke's law, after Hooke. And the force law in this case is simply given by F is equal to minus kx. This tells us that the spring force, which acts on an object attached to its free end, is proportional to the displacement of the free end from its resting position, non-stretched, non-compressed position, from its relaxed position. It's dependent. It depends on how much is the free end stretched or compressed. What is the displacement of the free end from the relaxed position, whether it is compression or stretching, doesn't matter. And it is so the force is proportional to that. The proportionality constant is called the force constant K, and the negative sign indicates that the force is always in an opposite direction to the displacement x of the free end from its relaxed position. This is an object attached to the free end of a spring. K is the spring constant, and x, which is defined by the dotted line, is the displacement of the free end of the spring, and 0 defines the relaxed position of the free end. So x is the displacement from the relaxed position, and k is the force constant of the spring. Now, since the force of the spring is variable with x, and the object is moving along the x-axis also, so we have a one-dimensional case with a variable force. So we can apply the previously developed definition for the work, which is the integral from the initial position of the free end where the object is attached to the final position of the free end of the force f of x, which is minus kx in this case, dx. This is a simple exercise, and we can evaluate this integral directly. And the integral is simply 1/2 kx square. 1/2 kx square with a negative sign taken from x initial to x final, and the result is 1/2 kx initial square minus 1/2 kx final square. That is the work done by the force of the spring. Now we move to another topic, which is defining the rate at which work is done. So far, we have been discussing the work done by a force. Sometimes it is not only the amount of work done or the amount of energy transfer that occurred is important. It's also sometimes important to know at which rate is the work done or the energy transfer has taken place. At which rate? Like, for example, to carry 10 chairs, for example, from one place to another, there is a difference between carrying the job during a period of 1 hour or carrying the job during a period of 1 month. There is a difference in handling the job, and sometimes this difference is of importance, and in that sense we talk about the power. So when we are driving the car or handling a given job, we care about the power, the rate of doing work. As usual, we first define the average power. If a force acts on an object and it does work W during a period of time delta t, suppose that delta t is the time that is required to do the job W, then we define the power of that force which did the work W. We define the average power during this period of time delta t as being P, capital P bar, which means average, is equal to the work done during the time interval divided by the time interval. This is the rate at which the work is done, but it is the average power because it is the average rate during time interval delta t. Sometimes we are concerned with the instantaneous power. That means at a given moment, what is the power of a given machine or a given agent that is delivering energy or that is doing work. And in this sense, we talk about the instantaneous power. The instantaneous power is derived from the previous definition of the average power, as usual, where we can calculate the average power during a time interval delta t, and then we can take the time interval delta t smaller and smaller, getting it smaller and smaller until it reaches a value of about 0, until it goes to 0. In this case, we call delta t an infinitesimal time interval dt. And during this period of time, which is dt, we assume that the force does work equals to dw, just a small amount of work. It does a small amount of work during the period dt. So the power in that case is the rate at which work is done at that moment, which is dw, the work done during that moment, particular moment, divided by dt, which is the length of that moment of time. Of course, moment doesn't mean 0 time, 0 interval of time, but as we get this interval of time smaller and smaller, if it approaches 0, the closer the time interval to 0, the more accurate is the power calculated, the instantaneous power calculated. And now from this definition, we can obtain another formula for the power, which relates the power to the force acting on the object and the velocity of the object. That is a more obvious form of the power, in which the force that is acting is obvious in the formula. The power is given by the force vector acting on the object multiplied by dot product with the velocity vector of the object. F dot V is equal to the power, and this is the instantaneous power. That is the power at which moment the velocity of the particle is V, and at which moment the force acting on the particle is F, because during the course of the motion of the particle, both F and V could be changing. So at that moment where F is working and velocity is V, that is the instantaneous power. This instantaneous power, which is related to the force and velocity, can be obtained from the previous definition, dW by dt. If we only remember that dW is simply the force dot the displacement dr, so F dot dr gives the work during a short period of time dt. And if we divide that by dt, so we will get F dot dr divided by dt. And dr by dt is the definition of the velocity of the particle at that instant. So thus we get the power is equal to F dot the velocity of the particle. And we obtain this formula. Now, the units, what are the units of power? The units of power can be derived from the definition of power. The power is work divided by time. And work is energy. As we mentioned, it is of energy transferred. Thus, work has the same units of energy, joule, in the international system. And thus, the power has the units of the work divided by the units of time, which is joule per second. This unit is called W, watt. It is given a different name, watt. So watt is the unit of power in the international system of units. Now we move to talk about the potential energy and its relation to work. The potential energy is a second form of energy which is intrinsic in a system, a collection of objects, and it is associated with the configuration or arrangement of the different objects in the system. We said that the kinetic energy is an energy associated with the velocity of the particle, with the speed of the object that is moving. And it is connected with the object itself. How fast it goes is defines how much kinetic energy does it have. However, the potential energy is the energy associated with the configuration, which means that it is not connected with only one object. It is connected with a number of objects that are interacting with each other, because the configuration of these objects, the locations, the relative positions of these objects relative to each other would define this quantity, which is the potential energy. The potential energy is thus defined in the context of having several objects in the system interacting with each other. At this point, I would like to discuss one of the key issues in the context of discussing potential energy, which is the classification of forces into two types. Forces are classified into two types. One is called conservative forces. A conservative force, as the name indicates, is a force which conserves mechanical energy, which does work, but mechanical energy doesn't get lost. We don't lose mechanical energy during the course of doing work by conservative forces. And this principle will be talked about later on. So a conservative force is such that the net work done by the conservative force, if we take an object from one point to a second point and then back to the first point, if the net work done by the force is 0 in going around the loop, then we say that that force is conservative, which means that we did not lose energy in moving the object from one point to a next second point and then back to the first point. We did not lose any energy, and that's why we call it conservative force. It conserves energy of the system. It does not lose energy during the course of motion as far as we go back to the same point of the object or to the first configuration of the system. So if we change the configuration of the system and back to the initial configuration, if no energy is lost, no work is done, then we say that the force is conservative. This figure illustrates this concept that we just talked about. If we take, if an object moves from point A to point B along the green trajectory, for example, the upper trajectory, and then back from B to A along the orange trajectory, the lower trajectory, regardless of where the trajectories are, regardless of the shape of the trajectories, the net work done by the conservative force is 0. That is the definition of a conservative force. Alternatively, the conservative force can be defined in a different way. We can say that the work done by a conservative force on an object as it moves from one point to another, say from A to B, is the same regardless of the trajectory, regardless of the path, So moving the particle from point A to point B, taking the upper path, or taking the lower path, or taking the straight line between A and B, the work done in moving during the object's motion from A to B is exactly the same, regardless of the length of the path, regardless of the shape of the path, and regardless of the nature of the path. That is the definition, an alternative definition of the conservative force. But it's the same as the previous one. It's not a new definition, because when we say that the work does not depend on the trajectory, so or on the path, that means when we take an object from A to B, the work done is the same as taking the object from A to B during another path, if we switch this path, the direction of motion of this path, then the work will be negative. So the positive work done in the along the upper path would be equal in magnitude but negative in sign to the work done during the lower path, which means the total work done during the loop is 0. So the two statements are essentially the same. Now we take the gravitational forces and the elastic forces of the spring as examples of these conservative forces, and we say that the gravitational force and the elastic force are both conservative forces, because if the work done by gravity, for example, during the particle's motion from one point to another, and then as the particle goes back to its initial position, it would have the same, exactly the same speed, the same kinetic energy, and the net work done by the gravitational force is 0, because the work done as it's going up is minus mgd, and the work as it goes down is plus mgd. So during the total path, the total work is 0. And the same for the elastic force of the spring. So we have doing work would lead to energy transfer, because we say, as we mentioned previously, as an object goes upward under the influence of gravity, the gravity does negative work on it and it reduces its kinetic energy. So there is a kinetic energy lost as the particle goes up under the influence of gravity, and the amount of kinetic energy that's lost is mgd. The work is minus mgd. So the object loses an amount of energy that's equal to mgd in magnitude. Where does this lost kinetic energy go? Because we have a conservative force, which is the gravitational force. We are not supposed to lose mechanical energy. Where does this transfer of energy go? This transfer of energy goes as potential energy, because the configuration of the system, which is the object, Earth in this case, the object is interacting with the Earth through the gravitational force. So this system, the configuration of this system changes, thus the transfer of kinetic energy is transferred to the potential energy from the kinetic energy. Vice versa is the object. If the object is going down, then the potential energy, which is the configuration energy of the system, is transferred into the kinetic energy, and the kinetic energy of the object is increasing as it goes down. So work involves transfer of energy, and in a system with conservative forces, the work acts to transfer energy between kinetic and potential. So as kinetic energy goes down, potential energy goes up. As kinetic energy goes up, potential energy goes down. And this transfer of energy between kinetic and potential is done through work. And this energy transfer is reversible. In each case, the change in energy delta U is equal to minus W, because as we said, the work done by the force is equal to delta K, which is the change in the kinetic energy, but the change in the kinetic energy has the opposite sign of the change in the potential energy. That implies that the change in potential energy is equal to minus delta W. And at this point, I would like to thank you for your attention and end this lecture.